Welcome, kids. Welcome to physics class. And we are looking at section 18b, part 2, which is actually just two short sections. And then, but we have some homework to go over first. This is homework from the last 2 days. I apologize. I originally intended to put some of the homework on the previous video, but it's okay. So, chapter review questions, the first set that you all did, starting with number 1. What did William Gilbert mean by the word electric? And of course, by the word electric, he meant any substance that could acquire and hold a electrostatic charge. I'm not sure how I got an and in there. Sorry about that. All right, number 2. Why does amber attract dust in dry leaves after it has been rubbed with fur? Now, I'm going to give you a complete answer for this, or a fairly complete answer for this. Obviously, just like always, your answer may not match this word for word. If you're trying to match it word for word, pause and get it copied down. But let me explain it. Rubbing amber with fur establishes a charge on the amber. So you actually transfer electrons, amber to fur, fur to amber. Then that induces the opposite charge in the dust and the leaves. It'll either repel or attract the electrons not out of the dust and leaves, but to like opposite sides of the dust and leaves, which induces the opposite charge. And since opposites attract, then the dust and leaves are attracted to the amber. Okay. That's number 2. Number 3, what happens when electrified amber test rod is placed near an electrified glass rod? Glass rod is going to attract an amber rod because they have opposite charges. Whereas if you put an amber rod near an amber rod, you're going to get repulsion. Okay, these questions did come from your reading. I didn't talk about these. This came from your reading. All right, question number 4. How did two different electric fluid theories explain the differences between electrified amber and electrified glass? Okay, got two guys, Dufay, whose theory was that amber had a resinous fluid and glass had a vitreous fluid. So Dufay thought there were two different fluids and different kinds of electrics got different kinds of fluids. Franklin, however, theorized that glass had an excess of fluid and amber had a deficiency of the same fluid. So Franklin thought there was only one fluid, but that materials either had extra or not enough or not as much fluid. Now, just for the record, Franklin was much closer, except that A, it's not a fluid, it's actually a particle, electrons, and B, I think, if I remember correctly, he actually switched them, so the one that he thought had excess actually has a deficiency. But he tried. He got closer than Dufay. Number 15, an electric is any substance that can easily conduct electricity. That, of course, is false. It should store electricity, not conduct it. Glass, amber, rubber, and lucite are electrics. That is true. If two objects repel each other, you know they are both negative charges. That's false. They could both be positive instead of negative. And you didn't have to give the reason why, but it's actually good for you to know the reason why. So that's why I'm including it here as we go through them. Number 18, the magnitude of the fundamental charge is the same for positive and negative charges, and that is true. Number 19, when a charge is established on an object, the charge exists because electrons have moved to or from the object, and that is also true. All right, that was the first set of homework you were supposed to do. Second set of homework that you are supposed to do starts with question number 5. Let me turn my book again. What happens to a neutral electroscope when you hold a negatively charged object near it, and why? And they actually kind of tell you why and then what. The negative rod repels the electrons in the electroscope, which migrate down into the leaves, and therefore the like charges in the leaves repel and spread the leaves. So the what really is the leaves will spread. The why is because the negative rod repels the electrons, drives them into the leaves, and sets up opposite charges. Number 6, when you bring a charged rod near a negatively charged electroscope, its leaves separate farther. Is the charge on the rod negative or positive? And the answer is negative. And I didn't talk about this in class, okay, on the video that you watched yesterday. But a positive rod would have attracted electrons from the leaves, which would have pulled electrons out of the leaves, and that means there would have been less charge and they would have gotten closer together. Because they spread further apart, that indicates that it was a negative charge, drove even more electrons out of the little sphere at the top and driven it down into the leaves. And again, we didn't really talk about it in class, but it was in your book, and hopefully you were able to find that one. All right, number 7. You have 2 neutral conducting spheres. How can you give one a negative charge and the other an equal positive charge without touching either sphere with a charged object? And I went through this in class video yesterday. Now place the spheres so they are touching. Bring a charged object near one sphere, and it will induce one charge in the closer sphere and the opposite in the further sphere. And then you separate the spheres, and they will have opposite charges. So that's the technique. We talked about it yesterday. That was pretty straightforward. Okay, question number 8. Explain what will happen when particles of paper picked up by a negatively charged test rod gain electrons from the rod. So the paper bits are neutral. When they touch the rod, they will collect electrons, which will then repel them from the negative rod. Remember back in the earlier question, the paper bits are neutral, but it induces a charge by pulling. Let's see, this is a negative rod. So it pushes the electrons to the other side of the paper, makes the front side of the paper positive, pulls it up to the negative rod. Then they actually collect electrons, so now they're negative also, and poof, they get popped back off. I will just mention a couple of these questions, 8 and 9 specifically, are from the earlier section of the book, but they put the questions in an odd order. Anyway, so this was actually not something we talked about in class. This was something you read on your own. Number 9, explain why a charged electroscope will discharge over time if left to itself. And this kind of combines the two, but the answer is that water molecules in the air will conduct charge away from the electroscope, neutralizing it. Anything that's charged, if there are water molecules or other charged particles in the air or conductive particles in the air, will conduct charge away from a charged object, like an electroscope, and will neutralize it eventually. This is very important in question number 11, so we'll come back to that. But the electroscope will naturally lose its charge to the water molecules in the air. Number 10, what if anything happens when you touch the electrode of a charged electroscope with your finger? And a human body is a huge source or sink compared to the electroscope. So your body is compared to the electroscope an infinite source of electrons and an infinite sink for electrons. And so any electrons that are unbalanced in the electroscope will migrate back or forth and neutralize the electroscope. So if it has extra electrons, it'll give them to you. If it needs electrons, it'll take them from you, and you won't even notice it. I'm guessing there would be an electric spark, but as far as like your body, you wouldn't feel weird because you were suddenly negative or positive, because the number of electrons compared to your body would be very small, but it would be significant to the electroscope. That's why you're considered a ground, which I'm not sure if I actually mentioned that when we grounded our electroscope yesterday. I'm not sure if I mentioned the fact that your finger is also a good ground. All right, number 11, why is it advisable on a cold, dry winter day to touch the metal case of your computer before starting it or touching any other part of the system? And I kind of paraphrase this, what they said, but low humidity days means that charges will build up rather than leaking off into the moisture in the air because it's not there. So in the winter, especially where we live, there tends to be very low humidity in the wintertime, and so charges build up much more easily, which is why you tend to get electric shocks during the winter time when you touch a light switch, when you get in your car, if your car is not properly grounded, etc. But when you build up that charge has the potential to destroy sensitive computer components. And so you want to discharge it into the metal case, which is not sensitive, before you touch anything inside the computer, which could be very sensitive to electric charge. All right. True or false questions. Number 20, on humid days, charged particles lose their charges more quickly because of the presence of water vapor makes the air more conductive. Been talking about that. That's true. Number 21, uncharged electroscopes can be used to indicate the presence, sign, and magnitude of electrostatic charge on an object. That is false. You cannot get the sign, not from a neutral electroscope. There is a technique, which we didn't really talk about, but not from a neutral one. And the magnitude kind of, as in you can tell by how far the gold foil spreads. That's not a very precise measurement. Now, there are some that are designed to be more precise on magnitude. So the false is mostly on the sign, but like magnitude is not real precise, but there are some that are more precise than the kind I showed you guys. The book has an example, I think, of one of those. Number 22, induction of electrostatic charge requires only the presence of a charged object, not actual contact, to establish a charge in another object. And that's true. We call that induction. We talked about that. Number 23, if the distance between two charged particles doubles, the force exerted between them will be halved. We actually haven't talked about this yet. That's what I'm going to talk to you about today. I'm sorry about that. I didn't realize the true-false questions went ahead. Anyway, the force will be quartered, not halved, and we'll talk about that in a moment. And if two charges exert an electrostatic force on each other and one charge is twice the other, the larger charge will exert twice the force of the smaller charge, and the smaller charge will exert half the force of the larger. And that's false. The forces will be equal, and again, we haven't talked about that yet. So I apologize on both of those. Forced you to look ahead into today's lesson, but we'll deal with that here in just a moment. Okay, so let's move on now to our actual lecture, Chapter 18b, Part 2. And we're going to start with 1810, Coulomb's law. And they start out talking about Charles Coulomb and how he measured electrostatic forces very accurately with a silk fiber supporting a rod with metal spheres on both ends, and then a stationary sphere and the twist in the fiber, etc., etc. I'm not worrying about the experiment itself. But he was able, by going through that, to determine a couple of things. First one is that the force was inversely proportional to the square of the radius. Y'all are familiar with terms like that. So the force of between two charged spheres was inversely proportional to the square of the radius, and it was directly proportional to the charges. And so this is called Coulomb's law. And if you look at this equation that I have on the screen, the force of the electric is equal to K. K is a constant. We're going to talk about that in the next section. But you're typically we have K for a constant in direct and inverse proportional relationships. The two charges, Q is used for charge. Don't ask me why, because I don't know why Q is used for charge. But little q is used for small charges. And Q1 and Q2 are the two charges that we're talking about. And R squared is the distance between the centers of the two charges. And so the force of electricity is equal to the constant times the two charges. Notice the absolute value signs there, which eliminates the positive and negative charge on it. That doesn't come out of the equation. That comes out of your head. And R squared is the distance between the radius of the distance between the centers of the two spheres. Now, the force of Q1 on Q2 is equal and opposite to the force of Q2 on Q1. In other words, there's an equal force between the two charges, but in opposite directions. So if they are both positive, they will be repelling each other, but they'll be pushing each other away in opposite directions. If they're attractive, one positive, one negative, they'll be pulling each other in, but they'll be pulling in opposite directions, actually. So you get a negative sign. The book actually was able to do it a little bit easier. I did it in words because it looked really too hard to turn that into an equation on screen. I decided words were easier. Now, you'll notice this actually should remind you of something. If you look at the equation on the left and the equation on the right, we didn't spend a lot of time on that equation on the right. It's in an earlier chapter, and we didn't do a lot with it. We did just a little bit. And that's the force of gravity. And I have the wrong constant there. Instead of a K there, that should be a capital G. But I'm not going to worry about fixing that at this point. Sorry about that. That should be a capital G. Anyway, actually, I might fix it. We'll see. If it's fixed, you'll know I fixed it. Sorry, guys. Anyway, the two forces look very similar. There are a couple of differences. One of them is there's only one kind of mass, but two kinds of charges. So you don't have positive masses and negative masses. You only have mass, but you do have positive and negative charges. Second thing is that gravity is always attractive. Masses always attract. Whereas electricity, you can either have an attraction or a repulsion. Like forces repel, opposite forces attract. And so you have the force of electricity can either be positive or negative, and that's based on knowing the charges. Gravity is always attractive. But these are very similar to each other because they are central forces. And central forces have very similar equations. All central forces have very similar equations. So this is the key part of the part of the chapter I'm teaching you is Coulomb's law. And the whole point of it is how much force is there between two charges. And it's pretty much going to be plug and chug. Now, for units of charge, there's something called the electrostatic unit. And this allows K to equal 1. So 1 dyne equals 1, which is K, times 1 ESU times 1 ESU divided by 1 centimeter squared. So it now allows the units to come out very nicely, makes K really simple, except for the little fact that electrostatic unit itself isn't all that useful. The more commonly used unit of charge is the coulomb. This is the basic SI unit. Don't know if that was on our a list of 7 units. I think it may have been 7 SI units. But anyway, coulomb is the basic unit of charge. And they are defining it in this chapter as 6.24 times 10 to the 18th electrons. So that's a lot of electrons to make 1 coulomb. And with that as 1 coulomb, K equals 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So that's your K. You just plug it in place of the K. That's a experimentally determined number for K. Okay, now they're going to give us an example. Example 18.1. This is on page 424. And they ask us to do 2-point charges, 1 times 10 to the negative 6 coulombs each, separated by a distance of 0.1 meters. What's the force on each charge? This is basically plug and chug, okay? You put in the 2 charges, you put in the K, you put in the radius, you run it through, and you get the force. Then they make the force part B. Yeah, they decrease the distance by 10 times to 1/10 of what it was before. Plug the numbers in, run them through, and you'll notice the force went up 100 times, which is what we'd expect because 10 squared is 100. This is probably the important part of this equation. Let me go back up here just a second. Here we are. The important part of this equation is that when you double the radius, you're going to quarter the force. If you have the radius, then you will quadruple the force. It's squared and it's inverse. On the other hand, on the charges, as you double the charges, you double the force. It's a direct relationship. It's as simple as it can be. It's just increase the force, increase the charge, increase the force, and by the same amount, the same factor. With radius, it's inverse, so it goes the opposite direction, and it is squared. And you will need to know that. Okay, the homework problems include quite a bit of math. Hopefully that goes well for you. Good luck and have a good day, y'all.